Okay. So, let me try to give you a flavor of how to see these groups in a method called stereographic projection. I am sure everybody would have heard about stereographic projection. You can map things on the 3D onto the 2-dimensional plane, right. You can do this mapping, and what we are going to use is that the thing is, we put the molecule first to start with. Let us take one of the atoms of the molecule here, okay. And when I do the C2, so I am going to just concentrate on one atom of the molecule and I will do a C2 operation, okay. So, when I do a C2 operation and draw it on this plane, this atom will move to this. Okay. So, the claim is that if there is a molecule with both the atoms at these two positions, it will be the symmetry, C2 will be the symmetry of that molecule with two atoms, and the point group will have two elements also. Okay. So, now let us go to C2V. C2V, start with the atom, you do a rotation. So, then you do the reflection. If you do a reflection, you end up getting 4 atoms. Okay. So, this is one way of saying that the symmetry C2V, starting on one point, you can generate all the 4 elements of that point group C2V. Okay. So, the same way you can do it for dihedral group. I have taken the simplest case, we can do for complicated case. So, take the dihedral group, as I said, you have a principal axis here. Now, this principal axis is also C2, and then you have an axis in the, which I am shown by a dotted line and with these two hats put on it to say that this is an axis which is perpendicular to the principal axis. And you start, you take a point, when you do a C2 rotation, it goes here. When you do a D2 rotation, what will happen? It goes behind the plane, unlike your mirror reflection. Behind the plane I show it by a hollow circle. So, this symmetry is not going to be the symmetry of a water molecule. Okay. So, this is slightly different, it goes behind the, I am not able to hear you, that is right. Okay. Okay. So, just to show you more, C3, I can put these 3 hydrogen atoms here. Okay. If you take C3V, then by mirror reflections you can have one more element added here this way. If you do D3, it is this. Okay. If you do D2H, what happens? Every element you have to do a mirror reflection on the xy plane. Object in front of you goes behind you. So, that is why you have both plus and minus. Plus is for the filled circle and circle is the hollow circle. So, I put both together. Here if you see, I do a C3 rotation. So, the plus goes here, and then I do a sigma V reflection, which means you will have, sorry, not sigma V, this is the two-fold axis rotation. So, you will see that this element goes here and then this element goes here and so on. Is this clear to you? Okay. Yeah. Yeah. So, D operation is we over on top of this 2 pi by n rotation, you do a rotation about an axis perpendicular to this axis, that is all. Okay. So, if you take the ammonia molecule, so D3 will involve E C3 C3 squared, okay, and then you will have a U2, you will have a C3 U2 and C3 squared U2. Okay. So these three things you can see as if it is the, to start with you had one two-fold axis, just like in your ammonia molecule to start with you had one mirror plane, but then the other elements can be seen as new mirror planes, right. Similarly, you can see this as U2, U2 prime, U2 double prime as three two-fold axes, but all of them are in the xy plane and they will be perpendicular to the z axis. So, that is the D3, and in this notation D3 will correspond to n equal to 3. Okay. Yeah. So, what is your confusion? Now it is clear? Okay. Any doubts on the stereographic projection? Yeah. C3V. So, let us do it, maybe that will clarify for you. So, you have the axis which is the threefold axis of rotation, which is sometimes denoted universally as a triangular point at the center, and then you take either a filled circle or call it as a cross. Okay. If you do a 120 degree rotation, this one has to go here. Okay. If you do a 120 degree rotation of this, then this one has to go here. Okay. And if I put a mirror plane on this, okay, this object when I put a mirror should give me another one which is here on the same plane. Mirror plane has to be with this, it should be the, as I said, you start with some conventional mirror plane, you could put it along this also, you have to put it on the plane of symmetry. These three atoms, if it has a C3 symmetry, I can't put mirror like this, that is what you are asking. If I put it here, then this will give you completely different things, no. So, if I am generating a C3V symmetry, I make sure my mirrors are not arbitrary in the xy plane. Pass through the, so that you get back your elements back, right. So, if I have this mirror plane, this element will go here, this element will go here, and this element will go here. Yeah. Mirror plane is? I am not able to hear you, one of them hearing, yeah. Okay. So, the way you should view is that I have projected it, you can view this as if it is a spherical atom and the left region gets mapped to the right region in some sense, that is another way of view. Okay. So, here I am doing a 2D projection, that is why it is called stereographic projection, and the C3V symmetry, when you are doing it technically, this atom goes into this atom is what you would have looked into it, but as a point a group element there are 6 elements in the point group. To see that, we explicitly put it as if there are points and how it transforms under a C3V symmetry. Okay. This is all I am saying. Yeah. Yeah. Any other confusion? And similarly D3 will also have this symmetry, but then you will also have a two-fold axis symmetry, and then you start generating this one will go behind when you do a D2 rotation, and similarly this one is because of this one going here and this one will go here. Okay. And equivalently, as a planes of symmetries, after you have drawn the stereographic projection, you can see that there is one plane which passes through this, sorry not plane, D2 axis. This is D2 axis, this was one D2 axis and this one will be another D2. Is that clear? There will be 3 D2 axes. If you ask a chemist what are the symmetries, they will look at symmetry planes and symmetry axes. He will say that there are 3 axes, two-fold axes which are passing through each of the atoms, and then he will say that there is also a 3-fold symmetry. That is what he will say for a D3. If you ask him for a C3V molecule, he will say that it is 3 mirror planes and 1 3-fold axis rotation. Okay. To him, he will only look at this axis of symmetry and planes of symmetry. Is that clear? Yeah. Yeah. Win PPT, the last one, D2H. Yeah. So, if you do a D2H, so let us look at D2H also. Anyway, you can also do the D3H. So, this is D3. If you want to do D3H, you also have a mirror on the XY plane. So, when you have a mirror, this cross will go behind also, the behind one will come up and so on. So, that will be the, so in fact looking at these points you should know how many elements are there in D3H. So, D3H will have how many elements? 12 elements. Okay. So, that is the way you can also look at a glance and get a feel of these point groups. Now, I am not looking at any specific molecule, I am trying to generate all the elements of the set of the point group by putting in the axis of symmetry and the plane of symmetry to start with. I make sure that I start with axis of symmetry through the center of this stereographic projection plane, and plane or axis of or the two-fold axis symmetry to be something which is coinciding with or perpendicular. The plane coincides, contains the principal axis, or I am looking at a two-fold axis perpendicular to the principal axis. And then the other principal axis and all gets generated, but they can also be viewed as compositions of sigma v times C3 and so on. Is that clear? These are various equivalent ways of interpreting the group elements of a finite group in the language of symmetries axis and symmetry axis and symmetry planes of a molecule. So, I have just given it on the slide a D2H plane. Okay. In the process of doing it, you can see that these are equivalently you can. So, looking at this point group thing, a person will say there is a 3-fold axis symmetry and then one 2-fold axis, second 2-fold and third 2-fold. And here it will be like you will have one 2-fold axis at the center because it is D2, and then you have one and another 1 2, 2-fold perpendicular to it. Clear? And also in the picture, whenever you have a sigma h plane, they replace the dotted outside circle by a hard circle. Okay. So, looking at it, they should know what is the symmetry group they are looking at it. So, once they see a solid circle, they will know there is a sigma h symmetry, and then they look at all these points and these axes which are shown here, and they will know what are the elementary operations which are there. Okay. So, any book if you take, it will all be there, you can go and look at any book, this whole like a periodic table, or it is not specific to an atom or it's specific to a molecule, but generally point groups are shown in this shorthand notations. You can see if I write C4H, C4H has a 4-fold axis, okay, and then the outside circle is solid circle. Is that clear? So, these are all rotoreflection. Now, you do rotoreflection here. If you do rotoreflection, what will happen? H2S4, S4 if you want to do it, tell me how it will be. So, you have a cross here, the cross rotation would have made it cross, but I have to do a reflection about a plane. So, it will become backside. Okay. And again if I do a 4-fold rotation, it will come in the front, and then again I do it, it will go to the back. Okay. So, the rotoreflection is nothing but C4 times sigma H, and clearly you can see the diagram is not isomorphic to C4, you can never make it isomorphic to C4, right. It has an improper component, but can we do the order reversed? Can you do first sigma H and then a C4? If you do a sigma H on this, it will go behind, and then you do a C4, it will be here. So, in fact, this is going to be sigma H C4. So, S4 will also be an abelian group. Okay. So, ways of seeing it from the diagram. Is this clear? Okay. Okay, so those are the notations which are given here, and you can show that there is no distinction between S3 and C3H. Okay. C3H, whatever you have drawn here, if you draw S3, it will be exactly similar to C3H. Please check it out. Okay. And S4 I have already drawn for you. S6 again will be similar, but 6-fold axis symmetry. Okay. And D3 I have already discussed, and then you can also have diagonal planes, which is what is being discussed here. Okay. So, I will leave it you to check some of these things and play around a bit. Okay, so this I have already told you that some molecules with cubic symmetries can be present. Some molecules can have tetrahedral symmetry, but tetrahedron can be also seen by embedding inside the cube. Okay. So, just to give you a flavor of the tetrahedral molecule, I am just taking 1 or 2 examples to motivate you. If anybody is like into this, you should go and list all the molecules and look at how things are. In fact, they have these kinds of animation where you can see the axis of symmetries and planes of symmetries of the molecules. Okay. So, if you take this is the methane molecule, you can take it to be the methane molecule with the 4 hydrogen, and center blue one is the carbon, and then these are the C2 axis rotations, and there are 3 C2 axes. Okay. And there are 4 3-fold axes, each 3-fold axis is going between 1 hydrogen and carbon, CH bond. Okay. Oops, I thought the animation will come here, it will not. I had the animation also, unfortunately it is not coming here. Okay. So, see some of these molecules have this rotoreflections. Okay. Rotoreflection is S4, especially this methane molecule has an extended symmetry which involves sigma plane, mirror plane. There are 6 mirror planes. I will leave it you to check these things. I had this animation which was supposed to show you that. Here rotoreflection, what happens is that first you do a rotation, it does not go to the configuration, but you have to do a reflection on this plane and then it goes into the configuration. So, it is very beautiful. So far what have we done? I have tried to give you a flavor of point groups, and these point groups are again finite groups and they can be shown to be isomorphics to subgroups of symmetric group of degree n. Okay. And I have introduced what are the fundamental operations with which you generate those finite point groups, either rotation axis, reflection axis and axis perpendicular to the principal axis. And whenever you have an axis perpendicular to the principal axis, then you can show that Cn and Cnk and Cn n minus k will be conjugates to each other. And similarly, even if you have a mirror plane containing the axis, principal axis, then you can show that these are conjugates to each other. And I have left you to try and understand the conjugacy classes of the dihedral group and similarly the conjugacy classes of the CNV group. Okay. When n is odd, when n is even, what is happening? We have seen that the rotoreflection group is a abelian group, and you can also show that the rotoreflection Sn is not very different if n is odd. Okay. So, you can try and check it out, do S3 rotoreflection and do CNH and see whether there are any distinctions. Okay. So, these are things which I want you to get to feel about some of these by playing on the stereographic projections and understanding whether this is true, is this true or is this true, you know, I will leave it to you to check all these things. Okay. And the next thing which we are going to take up is to give matrix representations to all these point groups. Okay. For example, if you take C2V, C2V is a point group, you can write matrices in your XYZ basis, right, all of you know that. Identity element is nothing but a unit operator, right, and C2 is 180 degree rotation which will change x to minus x, y to minus y. So, the matrix will be having -1 in the first two and then the C2 will z axis is unchanged. Sigma xz will change y coordinate to minus y coordinate, x and z will unchange, and reflection in the yz plane will change x to minus x, y and z will be unchanged. So, this is what we will call it as a matrix representation for the same C2V group. C2V you can write a multiplication table. The same multiplication table will be satisfied by the matrices, right. So, we give a representation especially the representation which we are going to look at is matrix representation, because one is that we can do the composition, the group operation as multiplication, and you also know that how you can operate it on vector spaces. Suppose this one is a 3 cross 3 matrix, you can treat this matrix to be operating on a space which has x, y, z coordinate, right, and you know what this answer will be. Suppose it is a rotation by 180 degrees, right, you know the answer has to be minus x minus y and z. Am I right? No. Is that right? Yes or no? And what is the matrix which can generate that state? If you try to find, then you know it is minus 1 0 0. Okay. So, this is what we will call it as a C2 element, and similarly all the other elements can be written. And clearly once I have written this, the properties which you have, if you multiply sigma v with the sigma v with C2, you will get one of those elements which is C2 sigma v, and you can verify that. Those are the other two mirror planes which you have. One mirror plane was sigma v, C2 sigma v is the other mirror plane. So, you get the other mirror plane. Okay. So, how many classes are there here? How many conjugacy classes are there in C2V? It is an abelian group. It is a class, every element is a class by itself, right. Once it is an abelian group, similarity transformation does nothing. So, there will be the order of the group itself will be the class. So, let us write for C3 the matrix representation. This is something which you all know how to write. R 120 degrees, which is what you call it as C3, matrix will be cos 120, which is sin 30, is that right? And C3 squared is right, and then let us write sigma v also. Let us do C3 sigma v, C3v. Sigma v will be, let us take it to be in the yz plane. Then you are all with me? And now you can generate other elements of the C3V group. How do you do it? You just multiply things. You multiply this with this, C3 squared with this, right. You can start generating the other two elements, right. Once you have a sigma v, you start multiplying and see how many non-trivial elements you get, and you generate a representation, a matrix representation for the C3V group. After we have got the representation, we would like to see what is the irreducible representation. Okay, that is the next topic. Okay. So, there will be an irreducible representation. What does irreducible mean? I can't further break it anymore. That is what is the meaning of irreducible. So, I need to find some set of non-trivial irreducible representations for each of these groups. Other thing you have to also realize is, if you take the trace of this matrix, trace, this is 2, right, this one is also 2. Right. These two are conjugate elements. Conjugate elements will share the same trace. So, your representations which you write will also have that property, that the trace within a conjugacy class cannot change. Okay. So, this trace, and if you multiply this with sigma v and write, that trace should also not change. Okay.